Well, welcome to workshop for this week. So we'll get straight into it and see what we can do. All right, so we sometimes have an opportunity using calculus to to find out some details about a particular function. Now I'm going to do an example straight off the bat, just so that I can make it clear to you what we're doing. But if we have this function as graph, what is the function polynomial? What is the polynomial of this thing? It's going to be rather complicated. So what that means is that we can sketch a curve like this using calculus. Okay? So this section is about curve sketching with more advanced polynomial style problems, and we'll have a look at some problem solving and modelling. They call that optimisation, but we need to learn a little bit about this first. So the first thing I'm going to do is posit a particular function. So here we've got a cubic. Now I could run off with Wrk1 and develop a graph of this, but I'm going to do it here using these techniques. Okay, so step one is that we'll want to assign the derivative to 0. What does the derivative assigned to 0 mean? Well, what it means is that we will find x values where m is 0. We will find x values where m is 0. Now, this makes perfect sense because the gradient is m, and setting the derivative is m to 0, we will find x values. Okay, so that's step number one. Step number two, so we will have to do some solving of that. So we will set that, we will solve this to get those x values. Y dash is equal to 0, and I'll show you what that means. The next thing we'll have to do, of course, is we will have to locate them, and that means finding the y coordinate. Okay, find the y coordinate. So we'll find the y coordinate, and we'll have to use the original expression for y and use function notation. So we'll be using function notation, f, or if you like, y of some value x, and that will give us the y value, the f of x value. And then we'll have a coordinate pair, x and y, and we might have a few of them. There could be a list of them. Okay? And at those points, m is 0. So that's not much information, and I'll draw that out as we go along. The next thing we'll want to do is understand their nature. So once we locate them, we want to know what's happening before m equals 0 and what's happening after m equals 0. Now, there's a number of different ways to do this, and we'll see a few different ways, but one of the things that we can do is find the derivative, the second derivative, and we can test at those found x values. So a little bit of work to do. It's a fairly involved process. So we'll test at the x values, and the final thing to do is to set the second derivative. I'm changing it deliberately to 0, and then solve. Okay, and that will give us an x value where the curve changes. And we'll come back to step 5. Okay, so for step 1, what we want to do is we want to take this derivative and take this function and find its derivative. So very straightforward skills that you've been using. Very straightforward. Times 2, x 2 minus 1 is 1. That one doesn't have it. So we've got 3x squared minus 6x. So we get our derivative. Now, that's this bit, but we want to do this bit. We want to set it to 0. Okay, so we want to make, and we do that by doing solve. So this is our second bit. So we've got 3x squared minus 6x is equal to 0, and we're going to solve that just like we solve any other particular equation. Now in this we know it's a quadratic. We could use the quadratic formula to do that, but because there's only two terms, we can take out what's common. So we can take out a 3 and an x, and we can take out x, because on expansion that would make 3x squared, tick, and minus 2 would give us 6x, tick. So that's our solution set. So from that we can draw out that we have x is 0, isn't it? This is true when? This is true when x equals 0, because that 0 multiplied by the brackets makes 0, tick. It's also true when the x minus 2 part is 0. Okay, so the x minus 2 part is 0, so x would have to be plus 2. So there are our two solutions for the derivative. Now remember that when we use this normally, solve of an equation gives x-intercepts. That's the roots of the polynomial. This is a slightly different idea. Okay, x-intercepts. So we want to be sure that when we're doing this, we're not doing it just on the y, because that would tell us where it cuts the x-axis, solve. We want to do it on the derivative, because that tells us that m is 0 on these two locations. Okay, now we don't know much about this curve at all, but what we do know is that in the graph, somewhere on m is 2 and 0, and I'll just pop down and come back up a couple of times. So we've got a graph, and what we do know is that at 0 and 2, somewhere here, there's a point that's got m0. Somewhere on this y-axis, which is the 0 value for x. Oh, well, it would be nice to know exactly where the point was. Where is the point that m is 0? So we use our function notation to find the y-coordinate. So we're actually going to test for 0 and 2. And they will give us the location. Now this f that we're using is this one up here. This is quite a bit of work, isn't it? There's a lot of stepping around different ideas. Whoom. So we've got to use function notation. So let's try 0. I'll do y because that's straightforward. That's what we've been doing. We'll use function notation on the graph. Not the end of the world. Function notation, let's everywhere there's an x, we will put. So this is the original now. What are we doing here? We're finding the y coordinate. Okay, so everywhere there's a 0, everywhere there's an x, you put a 0. Now they're all 0, so that means the y coordinate is 4. So we've got an xy pair of 0, 4. So if we just scoot down here, we can see x is 0, y is 4. Aha! So what we've established, and all we've established, is that m equals 0 at y equals 4. That's all we've established, nothing else. We haven't established its nature, only that there is a point on the y-axis at 4 that has a tangent, or an m, of 0. There it is, at 4. So let's do the other one. We've got a 2 we can put in. This one will probably mean we've got some work to do. So 2 cubed minus 3, 2 squared, plus 4. 2 2s are 4, 2s are 8. 2 2s are 4. 4 times 3 is 12. And so we've got plus 4. So 8 and 4 is 12. So we've got 12 minus 12. Now that was unexpected, but the y value is 0. So what we go to here on the graph is we go to x equals, so there's our pair, our pigeon pair. So I could put it up here now and put in at 2 we had y of 0. So they're our 2, aren't they? They're our 2 coordinates. So if we go along to 2, 0, 2, 0 is here. And what we know is that there is a tangent. Now I'm just exaggerating off the x-axis, but of course it would be sitting clearly on top of the x-axis, but that point there is a tangent. M equals 0. So we've got these 2 points, odd points that they are. I might just give them a little bit of a circle, just a little bit of a colouring, just to show that those 2 points have a tangent, and the tangent is M equals 0. All right, the next thing we want to consider is what's the nature of these guys? What's happening before the curve? Is it coming down like this? Is it going up? Does it go down this way, or does it come down from the top here? What about this one? Does it slide down, or is it coming up from the bottom? So we don't know anything about that. But one of the ways that we can establish that is by step. Where's our steps gone? Oh, I started way down the page, which was funny. Okay, so our step 3 is locate. Step 4 was then nature. And step 5 was to do the double derivative. So we've got to test the values at x. Okay, so we've got to take the second derivative now. So the second derivative, if the first derivative was, what was the first derivative? 3x squared minus 6. 3x squared minus 6. Okay, the second derivative will be 3 2s are 6x, and that one loses its value, so we get 6. So we get 6x minus 6. And because we're checking the values here, 0 and 4, well, 0 and 2 are the 2 values we want. Okay, because we're checking those values, we can use function notation. So y double dash, function notation, let's check it at 0. That will give us 6, 0 minus 6. Now 6 times 0 is 0. So we get negative, and look what I'm doing. I'm silly sometimes, aren't I? That's a big minus. Oh, wonder what that means. We'll come back to that because I want to test the other value. Y double dash, and this time we're testing it at 2. So we've got 6 lots of 2 minus 6. Now that's 12, isn't it? That's 12. So we've got 12 minus 6, which is, look, I'm being silly again. I'm exaggerating it because it's important. Plus 6. All right, well, it turns out, without proof, what I'm saying to you is that it's concave down here. A sad face, concave down. That's the shape of a concave down. And for the plus, we get a smiley face. So it's concave up. And in a nutshell, everything that we want to do in relation to this is now done. There's only one other thing to do, and that's the step 5. So we can go with some certainty to 0 now, and we can confirm that at 0, it's concave down, so it's doing this. We can confirm that. We can go to 2, and we can confirm, because of the second derivative test, that we've got it going up. Okay? Now, that's not much of a sketch, is it? It's not much of a graph. You've got bits of it. Well, calculus has given us an indication of what this curve looks like. That's the power of calculus. But we're not done yet because we've got to do step 5. Step 5 was solve when double derivative is 0. Okay, so the double derivative comes in the form of the solve because y double dash was 6x minus 6. So we can do 6x when we solve something. Now what's the difference? We're using the word, we're finding the roots or the solutions, but in this case it's not the x-intercept, it's other information, isn't it? So we need to be careful of that. So we just undo. And what you do to one side, you do to the other. And undo. And so at x equals 1, we have what's called a point of inflection. Now, I haven't even used the formal language about all these points. I've just been going ahead and doing an example. Okay, so an inflection, and that is where it changes concavity. So it swoops down, or like this, or it could be swooping that way, or it could be swooping up, okay, or it could be swooping up the other way. So generally that point of inflection sits there like that, and we can identify that's the very moment in the graph, in the life of the object, where you get a point of inflection. Okay, all those points there are points of inflection. Now we don't know where it leaves its address, but we can put it into our function using function notation. Okay, back to the original, and we can put in 1 cubed. Everywhere there's an x, we can put a 1. Okay, times plus 4. So we get 1 squared is 1, 3, so minus 3 plus 4. So that gives us 5 minus 3 is 2. So the point of inflection has an xy coordinate of 1, 2. So we've got to dress that up. So at 1, 2, x is 1 and y is 2. So there's 1. I've drawn these a little bit out of scale, haven't I? 2 would be about there. And so at this point here, this comes down like this one, and then it changes curvature like that. Okay, I might just fix that up. So we get that change of curvature, swoop. Okay, so that's a point of inflection. So look at that, we've joined it up. We've done very well. Okay, a point of inflection. Now all of these points, these wonderful points, have a special name. And the special name is, they are all part of stationary points. And so we've got stationary points, and from that we can get turning points, and from that we can get inflection. Okay, so it's a little class of business that we can do. So in a nutshell, informally, there's the process that we do. And look, we've actually done really well. We've sketched this graph quite a while. Now what we can do, because we know it's a polynomial and there's a repeated root here, we know that as a cubic is going to head off down here, and it's going to head off up here. Now what we don't know, apart from this one here, we don't know what that is. Now in this subject, you won't be asked to do a solve on a y, because that would give you the x-intercepts. Okay, in Maths 1 you will, so you'll learn how to do that. You'll learn how to solve a cubic, because we know how to solve. Just not going the way I want it to go. We know how to solve quadratics. We know how to solve linears, E and Lin. We know a whole bunch, but polynomials present a new skill set, and so there'll be some work done on that. Now I will put into the tutorial some solving of polynomials. Look at that. The calculus has said, here's your rather complicated polynomial. Now use calculus to show me what it looks like. Fantastic. So we've got to learn the formal language of that, and we'll return in the next video and do just that.